Good evening. I'm Sunny Shell, and this is the Crucible on the Promethean Secular Frontier, where we discuss science, philosophy, and reason from a secular perspective. And I'm really excited tonight because we're going to be discussing space and the infinity. And so I'm going to go ahead and bring in our guests one at a time and let them tell you a little bit about themselves. So the first one is Duccio. Did I say it right?
Perfect. Yeah, Duccio. Hi.
Mucho
Hi,
Duccio.
everybody. My name is Duccio. I'm a PhD student in astrophysics in Italy, in Bologna, at Bologna University. And basically, I work on some kind of galaxies. I observe and study some kind of galaxies which are found to be active, in the sense that at the center of these galaxies, there is a huge black hole which is eating matter, and they are called active because this accretion produce a lot of structures around the black hole which are very powerful, and we can study them through our through telescopes in different bands. And so basically I've studied astronomy as bachelor as my bachelor degree, and then astrophysics as master degree, and now I'm studying active galactic nuclei within my PhD.
That's awesome. And can I just say I love your accent? I'm just going to be enjoying listening to you all night.
Thank you.
The next one is someone that we have seen on our show before. We have David, and David is a very loved person on our show. So welcome back, David.
Hi, how are you?
I am great. So if you will remind people who you are and what you do.
So I'm a physics professor, and I also study black holes. And when I originally started, I explored black holes from a slightly different perspective compared to Duccio. I explored black holes very close to the black hole to try to figure out how black holes produce these enormous amounts of energy that we see and that Duccio observes on large scales. So that's a little bit what I do.
Wonderful. I'm so glad to have you back.
Thank you.
The next one that we're bringing on is Chandra. And welcome, Chandra.
Yeah, thanks. Hello. Hello, everyone.
So tell us a little bit about yourself.
Yeah, so I'm Chandra, working as an associate research professor in southwest of China in an astronomy institute. And so my work has been mainly related to the phenomena around black holes using some theoretical as well as simulation techniques. And I would like to mention that David and I have been collaborating since last more than 5 years. And so there is some overlap between his and my work in this direction. Thanks.
Wonderful. Well, welcome. And for all of the guests, I really hope that we see more of you on our channel. Next coming up is Emily. Hi, Emily.
Hello.
Tell us a little bit about yourself.
Well, first of all, thanks for having me on here. So my name is Emily Moravec. I am a postdoc at Green Bank Observatory. It's a very special place in the middle of West Virginia. And I'm a radio astronomer, and I study the active galaxies that the others study as well, but I study them specifically in the radio wavelengths of the spectrum of light. And I also really enjoy studying how galaxies interact with one another when they live in groups called galaxy clusters.
That is so exciting. All of you guys are just making me geek out. I wish that I had the knowledge that you guys have. What an amazing group. The next one we have is Tanner. So
Hi.
Thank you for coming on, Tanner.
Well, thanks for having me.
And if you will tell a little bit about yourself.
Let's see. I teach physics at Truman State University in Missouri. And actually, my interests are these days more in the history and philosophy of science. I'm particularly interested in, say, fake science and paranormal claims and things like that. My latest book has a title of Weirdness with an exclamation part at the end. And my physics background, unlike every one of your guests over here is not in astrophysics. In fact, right now I'm teaching a cosmology course, and the reason I wanted to teach a cosmology course it's the best way to learn something. So I knew nothing, therefore I wanted to teach it.
That's awesome. That is so cool. I just want to say that is a very important thing to be talking about, especially today. If we believe in woo and paranormal and all of that, what will that mean about how we, what other things that we believe? It kind of impacts that. It also impacts our behaviors and the decisions that we make. So I'm glad that you're out there doing that. Thank you. So tonight we're talking about space and infinity. And the first question that I wanted to ask you is, does infinity exist in space? And let's start with Duccio.
I want to talk from the observational side, because it's that then I know better. The universe is not infinite from the observational side, in the sense that we can, there is a definition of universe horizon, in the sense that the light is traveling at a finite speed. So we know which is the speed of light. And then we can see only the light that has traveled toward us since the Big Bang, which was 13 billion years ago. Then the universe from the observational side is finite, is not infinite. Then the theory from the other side, if the universe can be finite or infinite, it depends on the on the shape of the universe, on what we call the shape of the universe, because the universe can be can have different shapes. It can be closed, and in that case, it is finite. It can be flat, so flat geometry, and in that sense, it would be infinite. So the answer is quite complex, but from the observational side, we can say that we can only observe the universe is finite.
And I would love for anyone to just jump in if you feel the need. And if not, if no one answers, then I will pick on one of you. So if anyone else wants to answer.
I'd be happy to jump in there. So Duccio is using some pretty strange words, and you're talking about the shape and the space, and it might be useful to point out that 120 years ago or so, we had no real constraints on what space is like. So when you ask the question, what is space like? Is space infinite? There were really no constraints. But after Einstein put his theory of general relativity together, space and time are sort of constrained by the stuff that's in the universe. And so we can ask questions about what space is like, what is the shape of space, whether, like Duccio said, the space is flat or not. And that depends on whether there's a certain amount of matter and energy in the universe. Because what Einstein's theory tells us is that space and, in fact, time are shaped, they're curved, as the theory, the terms that are used in the theory are curved by the distribution of matter and energy in the universe. So, so it's actually a much more interesting question than it was over 110 years ago.
I'm really glad that you brought that up and kind of explained things, because as someone else had put in the chat, it's like, that's interesting. I want to hear more about that. What do you mean open, closed, flat, all of those things? Let's see, Tanner, what do you have to add? Do you have anything to add?
Oh, sure. I'd like to point out that certainly observationally, we can only see a finite amount. But our current cosmological models tend to indicate that spatially it could very well be infinite. We just are not in contact with it. And also another thing to keep in mind over here is, particularly since we're talking about the historical aspect of cosmology, cosmology is a fairly new area of physics. And one of the things I like to impress upon my students in cosmology is it's not an area of physics where you can have quite the same amount of confidence in what you're saying as, say, the physics of transistors. The physics of transistors, you can bet your life on. In fact, we regularly, all of us do bet our life on it almost every day. But cosmology has much larger uncertainties, and indeed astrophysics in general. So when we're talking about whether the universe is finite or infinite, all of us listening to this have to be kind of aware that we're doing a certain amount of hand waving over here, which is okay. I mean, science is about managing uncertainty, among other things. And when you're in the field, you're used to dealing with it. But you don't want your listeners to get the idea that we sort of absolutely know what we're talking about. It's not necessarily the case.
Emily.
Oh, I think my colleagues have done an excellent job of trying to portray something about these very big words of, you know, infinite and space. And so I also come from the side of observational astronomy. So I'll just give a bit of background on that. We kind of do separate in astronomy and astrophysics between observational astronomy, which is where you have those that are using telescopes to measure something. And then you have those that are working in theory, trying to understand what could be. And it's really wonderful to have crosstalk between the two. And that's how we really, truly learn about our universe, is melding those two together. So I also come from the observational side. So I thought my first thought was definitely, well, yes, it's finite because that's what we can see. And as telescopes get better and better, we can see further and further back in time for the universe specifically. But something I was also thinking about is that some of our favorite topics are black holes. And those are a very special part of math and physics, that they have a lot of infinite things about them themselves. So my answer would be that, to me, the universe is finite as we see it now, but there are a lot of possibilities, but there are a lot of infinite things inside of the universe too, which is really fascinating.
Thank you so much. I now have questions, so we'll get to that in just a second. I want to go to Chandra. Do you have something you would like to add?
Yeah, like Emily mentioned about black holes, and so when we study black holes specifically, then we don't come across anything like infinity, rather a large number, I can say. For example, in terms of velocity, we can have matter approaching maybe the speed of light, that is like 300,000 kilometers per second. And in case of temperature, we can have high temperature like 10 to the power 9 Kelvin or 10 to the power 12 Kelvin. So we don't really deal with infinity, but a very large number in some sense, yes. So, yeah.
Okay, so now this brought up a couple questions that I wanted to ask you guys. So the first, well, not really questions, but more streams. One thing that that you said, Emily, was that we see only so much, and as telescopes get better and better, we can see further and further into the history. And I wanted to kind of just touch on that because everything that we see is historical. We're seeing what the further back we go, the further back in history that we are going. And I just wanted you to explain a little bit more about that, because I found that interesting when I was say a college student and trying to wrap my head around all of that. And so I'd love to kind of have a little bit of a discussion, if we could, just about that.
Yeah, absolutely. I think as astronomers, astronomers just get very used to thinking about that you are looking back into time and you are understanding the history of the universe. And it goes back to the basic physics that Duccio is talking about. So light travels at a finite speed, and we are dealing with a very large universe. And so it takes a certain amount of time for light to travel specific distances. So what I remember is, if you think about it in terms of the solar system, I think it is, I know that Saturn is, when you see an image of Saturn in a telescope, you're seeing it as it was several hours ago, in fact. The same with the sun. And then you go further back with Pluto. So Pluto, so I believe Saturn's like 90 minutes, you're seeing it as it was. And then Pluto, you're seeing it as it was 9 hours ago. And then the closest star is, I think it's about 3 light years. So when we observe that star, at one moment, you're seeing it as it was 3 years ago. And then the next closest galaxy is much, much further. And so as you see something that's farther away, you're also seeing that light as it was at that time. And so that's how we study the evolution of things in space, is we will look at things at different distances, because that is equivalent to looking at things at different points in time. And so that's how we can kind of put a cosmic scrapbook together to look at things at how they are at different points. And it's all based on this idea and this very basic physics principle that light takes a finite amount of time to travel a certain distance.
And does anyone else want to jump in on that particular topic?
I wanted to maybe ask if it might be interesting to ask what is the most distant object that we can observe, and maybe Duccio and Emily, you guys are better than us at answering that question.
Yeah, I keep losing track because we keep getting to see something further and further. I believe something the furthest back that we have seen, astronomical units, is a redshift of about 7 or 8. Now that is a whole thing. And so I actually don't remember what that translates into light years, because we work with such large distances. We work with a different unit. But I believe, it's a very small fraction of how large the universe actually is. I need to memorize all those numbers of how far each thing is.
That's such a great question. Anyone else want to jump in with?
Well, I mean, if you want to add a detail, it's not a matter of our knowing the distance of the farthest observed object. The idea is that astronomers usually talk about these things in redshifts because that's what they observe. And translating the redshift to an actual distance is actually complicated. It's very much depends on cosmological models, because the redshift, a large part of the redshift that what we're seeing is cosmological in the sense that it's due to the expansion of the universe. So if we're looking at an object out there, figuring out the exact distance between here and the object, given the redshift, which is the main piece of data that we have, is actually a tricky proposition. It depends on cosmological models.
Oh, that's fascinating. Oh my gosh, that's so fascinating. So we did have a couple questions from the audience I want to take while we're still on this particular topic before we move on. Cease to Know asked, how would you respond to William Lane Craig's claims that infinity is contradictory or paradoxical?
He's talking through his hat.
That's the best answer. That is awesome.
I would say that infinity is everywhere in physics and astronomy.
Yeah, it's a mathematical object like any other. Objecting to infinity is sort of like objecting to 0 or 1 or something like that. If it works in explaining something, fine. I mean, I can give you all sorts of strange examples in physics. Say, for example, in a system where you have spin temperatures, you can easily go through infinity by increasing the temperature. You can go through infinite temperature and actually go into negative temperature areas. And there's nothing wrong with that in physics.
Very good. That was probably the best answer. Yes, David, I think you look like you wanted to say something.
I was just going to comment that, we're not philosophers, and we're not going to be able to I don't think philosophers can do this either. They can't give us, the ontological status of the concept of infinity. I'm just pointing out that it's necessary, and we wouldn't be able to do so much of what we do if we got rid of the concept of infinity.
Well, so does that mean that just like there are different terms for different things, could infinity in philosophy potentially mean something different than infinity in physics?
Yes, in a sense, there's actually a long history of mathematical thought on trying to define infinity, especially starting in the 19th century, when people first started inventing transfinite math. And it had people who generally actually invented these concepts of infinity have generally said that it's actually very hard to translate the mathematical concepts of infinity, of transfinite math, into our sort of pre-theoretical notions of infinity. So essentially, in our everyday concept of infinity, we don't really necessarily know much about what we're talking about. And translating that into mathematical terms is actually quite hairy, more than what you might think.
Okay, that makes sense. So our next big topic of discussion that I wanted to get into is about cluster galaxies. So I really wanted to talk a little bit about like what are cluster galaxies? How do we know that there are cluster galaxies? I mean, let's talk a little bit about that, especially what is a cluster galaxy or what are cluster galaxies? I don't even know if I should say it with in plural or singular. Do we call it a cluster galaxy or? So please, let's dive into that a little bit.
It's my favorite topic, so I can start it off. So there are a lot of different scales in the universe, and so we live in a solar system, and then we live in the Milky Way galaxy, and then galaxies can actually group together. So gravity works on very, very large scales. Not just on Earth and to keep us going around the sun and etc., but it can bring galaxies together, and they form groups or clusters. So we call those galaxy clusters. And so galaxy clusters are groups of about 100 to can be anywhere from hundreds to thousands of galaxies. And it's a very unique environment, actually. Because these groups and clusters of galaxies they have a lot of hot gas that's in between all of them. It's very, very hot gas. And you see these galaxy clusters, and their total mass is actually mostly made of dark matter. So this is the matter that we know exists, but we have yet to observe directly. And then the rest of the mass of that galaxy cluster is so 80 to 90% of the mass of a galaxy cluster is dark matter. And then you have about 10 to 15% is this hot gas. And then only about 1% is the galaxies themselves, which is what we actually observe. And we also observe that hot gas. And so it's really, really interesting because the life of a galaxy will be very different in a cluster than it will on its own. So it's the same way with humans. You know, if you live in a city, your life is very different if you're surrounded by a lot of humans as opposed to living out in the country by yourself. So what is a galaxy cluster? Well, it's a very massive object that has galaxies, hot gas, and dark matter, and it affects the evolution of the galaxies that are in the cluster. So a galaxy cluster is all those things, and then we call the individual galaxies cluster galaxies, cluster galaxies. It's kind of so you can use it both ways.
Do galaxies escape the cluster and become galaxies outside of?
That's a really good question. Not that we know of. They don't escape it. Usually it's throughout the evolution of the universe, things are coming together. So they actually coalesce. So they start at the beginning of time. They start not a part of a structure. And then as time evolves, you get more of a structure. So they don't usually escape, or that's not, they don't escape, but they actually all come together throughout time. It's a really good question. Yeah.
Yay, this is exciting. Let's say, Chandra, do you have anything that you want? I don't know if you guys, how many of you are actually into galaxy clusters like Emily is, but I want to open it up for the rest of you. Do you have anything else that you want to add to this? And Chandra, I'll start with you.
No, in my work, I have been focusing on galaxies rather than galaxy clusters, because my focus is on black holes, and so usually it is found that at the center of almost all galaxies, you found black holes. So in a way, I would say that there is a continuous process of creation and destruction going on. So there is a formation of a star in galaxies, while at the same time, the black hole is end state of a star, and also it takes in matter from surroundings. So so my focus has been to study, like, for example, our own Milky Way galaxy center, or M87 center, where there are black holes exist. And so I don't have any specific things to say about galaxy clusters. So I think Emily covered it well. So yeah.
Thank you. Anyone else? Anyone else have an interest in these galaxy clusters?
I don't do anything about galaxy clusters, but I have a question, since I do have an expert on galaxy clusters over here. About what scale are we talking about with the largest observed galaxy clusters? And one reason I'm asking this is, in cosmology, one of the interesting things that seems to be happening is that we generally make the assumption that at scales larger than about 300 million light years, the universe starts looking the same. But also continually, I keep hearing from astrophysicists, and I'm in no position to evaluate this because I'm not an expert, that you occasionally get evidence that with dark flow and things like that, there may be some structure at even larger scales. But we don't know. It's always controversial among astrophysicists, and I'm not an astrophysicist. So does our knowledge about galaxy clusters contribute to resolving questions like that?
Absolutely. So I was actually going to bring that up, because that seems to be in line with your interests too, that galaxy clusters are often used to test cosmology, to understand more about how the universe formed, because these different theoretical models for how the universe came to be and evolves tells you how much matter there is in the universe and how things evolve. And so it's really interesting to study at what point in the universe do you have a massive object. And that's a really good constraint on how the universe evolves. So to answer your question about the size, so I study galaxy clusters at a specific time in the universe. And so, look in the present day or in the local universe, so our nearby galaxies and such, they're usually about a megaparsec. I don't know what that is in light years, because I'm so used to
3 million light years.
Okay, perfect. Now I know that. Okay. Yeah, so they're about a megaparsec, but they can be a bit smaller. But it's another thing that a collaboration and I study is how far back do you see these really, really massive galaxy clusters? And that it can be used as a constraint to understand cosmology. So yeah, another exciting topic.
Oh, this is so exciting. Okay, I have a couple questions from the audience again. The first one is light a particle or a wave?
Yes.
So expand on that a little bit.
Okay. When you measure light, you can set up your experiments that you can essentially detect single photons. So you detect light as particles. However, the distribution of where you're going to see these photons involves waves. So light, you might say, is a particle that is described by a wave. And that applies not just to light, but every other particle we have.
All right.
was a bit about-
Anyone? That's pretty cool. I like that answer. Another question that we have: what evidence is there for an infinity being unable to exist in actuality? I'm not quite sure
Okay,
who to go to with that, but
Maybe I can comment on why infinity might bother us in some cases. For example, we have mathematical structures where, for example, the force of gravity between two objects. Mathematically, we describe that as what's called the inverse square law, and that means we're dividing by the distance between two objects. And of course, if that distance becomes zero, you're dividing by zero, you get infinity. And so it's hard to imagine that the force of between two objects that I can hold in my hand could be infinite. And the idea is that infinity is just sort of a mathematical quantity that when you look more closely, you need to resolve, and that infinity will go away. So there are places where infinity bothers us, and it's just that we weren't very careful with our theory, and those infinities need to be resolved. So it can be we can resolve these infinities, solve them, get rid of them in some sense, and this we see all over the place. In various theories, so you have infinities, and then there are nice ways where you can get rid of them, and then places where they kind of seem to hang around, and they're a little more of a problem.
Probably your audience might be interested in the kind of infinity that shows up in the cosmological context. For example, we're talking about the Big Bang. So the idea is that you go back in time enough, the universe starts from a very hot, very dense state. And if you keep pushing further, it looks like your density is going to infinity. Now, what the blazes does this mean? And right now, a physicist will have to tell you, we don't know what that means. We don't have a very good way of understanding something like the Big Bang because we don't have a theory of quantum gravity. And so we have a situation where we get an infinity in our theory, and it's bothersome not because it's infinity per se. As I said, infinity is just a mathematical object, but it bothers us because that just doesn't make sense in the context of what we know about other things in physics. So things seem to be breaking down, and we don't really have a good theory yet of quantum gravity that might handle it. So sometimes getting infinities in our physical theories can be a pretty good sign that there's something about physics that we don't know about, that we need new physics to be able to answer that particular question. So in that sense, finding an infinity can be quite useful.
That's fascinating. Okay, we have another question. What is the connection between mathematical objects and the quote real world? I get this. I mean, this is a difficult thing. A lot of times in physics and astrophysics and cosmology, we talk about things in mathematical context. And so maybe how does that translate?
Well, the way I like to approach it is mathematics. Think of mathematics like a language. So the connection between mathematical objects in the real world is not necessarily hugely different than the connection between an English description of an object in the real world. So if you're talking about a green apple, it's a non-trivial question how you're talking about a green apple in terms of ordinary language maps on to the physical reality out there. And math raises similar questions. But still, fundamentally, math is just what we use for description.
Now, I like that. I have heard of it being used as like a language. I'm sorry, David, you go ahead.
No, I'm sorry. I was just going to add that, this mapping is not always as direct as one might think. So, if I'm studying first-year physics and I do what's called kinematics, I'm dealing with velocities, accelerations, and the positions of objects, there seems to be sort of a direct connection between the math and the physical reality. Here's an object that experiences a force, it accelerates. And my theories, my mathematical equations are, there's a direct connection there with that physical reality. But then I can get into places where I have complex mathematics, complex variables and strange math that seems to not really map onto the real world, but necessary. Like, things I might need to take the square root of a negative number. And that's a very strange thing to map onto reality. And I don't see that direct connection anymore. And so I start to lose that.
Yeah,
so
and
it's
pretty much every physicist gets into this situation that you start out the situations where things are fairly easily visualizable. It's our everyday experience connects to it when you're talking about tossing a ball and catching it and things like that. But as you go deeper into physics, you quickly run into situations where your ability to visualize things just falls apart. And the most notorious example is quantum mechanics. Our brains are completely not suited for quantum mechanics. And this, by the way, is one of the reasons why there's so much math in physics. We continually have to push ourselves into domains where our everyday understanding is just completely unsuitable. And so we have to use math as a tool, but we also have to recognize that it's not going to be intuitive all the time.
That totally makes sense to me, because I think about, for instance, black holes, as Chandra is interested in. For a long time, we didn't know if they actually existed. It was the math that showed that they existed, but we did not actually have the evidence for them as far as being able to see them or to study them in that aspect. We just knew that there was the math that showed that there was. That kind of brings up another comment. It was not exactly a question, but it could be, that dark matter was theoretical, but it was in the math. Am I correct in what I'm saying? I know it's very layman and ignorant, but it was the math that really showed us a lot of the things that we now actually know in the observable reality, I guess. Is that correct?
Well,
yes, sort of.
Sorry.
No, go ahead.
No, I was going to say, Chandra, go ahead.
No, about the dark matter, I would say that it was the velocity profile of the galaxies, where it was found from observation that it is supposed to decay with radius as we go away from the center of the galaxy, but it was found to getting a flat profile. So the need of dark matter came from the observational results, actually, rather than the mathematical. And then people started thinking about how to explain this, and they have to introduce something called like a dark matter, which is different than ordinary matter. So in terms of interaction and the form, and we cannot it is called dark in the sense that it cannot reflect like light like an ordinary matter. So I think it is, rather than a mathematical need, it was an observational need to how to explain those things.
Okay, all right.
Basically, you have a failure of a fit between your explanations and your observations. And so something has to go. One possibility is that there's something out there that we don't see. We only see as gravitational effects. That's a dark matter as an explanation. So you say, okay, if you put this extra dark matter into the picture, then you can understand your observations. But the problem there is, of course, if the gravitation is the only effect that you see about it, you don't have any independent evidence for it. So it sounds like you just made something up to save your theory. And so you try and find other independent lines of evidence from, say, things like particle physics, which would also suggest that there are some particles out there that would have a purely gravitational effect and not, say, for example, electromagnetic effects. There are other options. Some people have also explored modifying gravity, which is a far more dicey proposition. Almost all astrophysicists will stay away from that option. But perhaps what your questioner means in saying that he thought that dark matter was still theoretical makes that sense, is that we think that there's dark matter out there in order to explain the observations, but we don't have direct evidence for dark matter. We don't know what it would be made of in terms of particles. There are a whole bunch of things we just don't know about dark matter. So in that sense, yes, theoretical.
Yes, the questioner is perfectly correct. No one's found this stuff. We assume it's there. I just wanted to point out that this is something that was really brought home to us by Vera Rubin, who was an astronomer who did these observations in galaxies. And I think these were hundreds of galaxies that she measured the velocities of stars, gas and dust in galaxies. And given our basic laws of gravity, F equals ma, you can calculate how fast these things should be going. And there was just these things were going too fast to be understood within that mathematical structure, given what we observed. There wasn't enough stuff to hold this stuff together. And so we've been assuming now, since the 1960s, as a family, Vera Rubin really brought these things home to us, late 1960s, early 1970s. We've been talking about dark matter, and people have been looking for it, but it's been now 50 years, and we haven't found it yet. So,
yeah, in fact, it gets even more complicated than that, in the sense that over the past couple of decades, one of the most prominent candidates we've had for dark matter have been connected to the idea of supersymmetry, that every particle we know about is supposed to have the supersymmetric partner, which somehow might be much heavier, and we can't detect it, and it does gravity, but it doesn't do electromagnetism. But we were supposed to be able to find supersymmetric particles with our accelerators, the most powerful accelerators that we have right now, at least in the most simple versions of supersymmetry. And interestingly enough, this is something that you haven't heard much in the news, because in the science news, you generally hear, oh, we've discovered something. Here's a new particle, the Higgs boson, the same thing like that. But probably one of the most significant findings in the last decade or so in particle physics is the fact that we've failed to find any sort of supersymmetric particles. So in a bizarre way, we almost know less about dark matter right now than what we might have done 10 years ago and what it might be. It's kind of interesting.
I think that's such a valid point to make. I think that that's a problem that we have on a bigger scale, is that things are not considered newsworthy or exciting enough, and yet they have a big impact on the way that we know the world around us, the universe and so forth. It's from these things, and it seems like they're not made accessible to people. Like, what I would like to know is, you were talking about that's not really made a big newsworthy. Where can people like me who want to know go to find that type of information out when something like that happens? So we have not made this discovery and we thought we would, or other things that really should make the news but don't. What are some places that we can go to find that stuff?
You're going to have a hard time. I mean, this is one of those things that it's big if you're in physics, but if you're outside of physics, it's the sort of the dog that didn't bark in the night. It's difficult to sort of write down a simple layman's paragraph explaining the significance of it, because the significance of it ties to so much other that's going on in physics. So it's difficult.
Okay, that makes sense. We have another question from the audience. What do you make of the argument that if the universe is contingent, it must depend on something outside of it to exist? Y'all don't jump in all at once. That must be a big one.
I would just say we have no right to make statements like that about
you will notice
that of the universe.
The observational astrophysicists are not jumping into questions like this. There's a reason for this. This is by and large a metaphysical question, not a physics question. And what physics may contribute over here is a note of caution, in the sense of what makes that argument that says the universe is contingent and therefore it must depend on something else. What makes that argument plausible is a reliance on our everyday perceptions of how the world should be. And if there's anything we've learned in physics, is that we really should not trust those intuitions.
So, that makes sense. Yeah. It's kind of like what you guys were talking about you can see so far back. The furthest that, and that was one question I was going to ask you guys is we can see further and further back, but we haven't been able to observe the history all the way back to the Big Bang. It's more kind of like there's observable, and then there's, I can't remember what term you guys used earlier, not theoretical, but not observable. And isn't that what the Big Bang, we say the farthest we can see back is the Big Bang, but have we actually been able to observe that far back?
That's a good question. I can go on this. Yeah, I'm much more on the observational side. So I talk about what I can see and what I see in the data. But the farthest that we can see back is something called the cosmic microwave background. And it's basically this thing that we see that's very uniform all across the sky at a very specific point in time. And it's at that point which the universe actually becomes, you can actually observe it. Before that, you cannot actually observe anything like yeah.
It's not transparent before that.
Yeah. Yeah. So we can see as far as that, but then theory has to take us with our telescopes. That's how far back we can see. And then the theory has to take us the rest of the way. But it is a good chunk of the way there. But yeah, so that can help us understand things, but it is a limit.
Okay, that does help.
It might be interesting to point out that everyone who had an old television with an antenna was detecting the microwave background radiation with those antennas. So everyone had access to that some years ago. Yeah.
Oh, that's
40,
cool.
50 years ago. Yeah. Maybe 30. Yeah.
That's awesome. Okay, so I have another one, and I know Chandra's going to jump all over this, but I want, and for all of you, please feel free to jump in. On black holes, what is Hawking radiation, and why can it escape a black hole?
I think, yeah, the Hawking radiation is something related to the what is called the evaporation state of black hole, and it is again I would like to mention that it is hard to observe because the temperature we are dealing with is lower than the CMBR temperature that was mentioned just now, like the cosmic microwave background radiation. So I don't know if there will be any kind of observational support in this case. So I don't know anyone else has to say about this.
Well,
I would just point out that it's.
I like
sorry,
to describe it. No, go ahead.
No, go ahead.
Yeah. Okay. One way I like to describe it is this, because I get this sort of student question from my students a lot. A black hole, your usual image is something that that matter, radiation, everything like that falls in and never falls out. But you can also imagine a white hole, which is just a reverse of a black hole. It spews stuff out. The interesting thing, it turns out that the black hole has a temperature that's related to its size. And the smaller the size of a black hole, the bigger the temperature. So if you actually go to a really, really small black hole, not the kind of black holes that my astrophysicist colleagues are talking about, the really, really small black holes, it turns out that they're actually white holes. They radiate because everything that has a temperature radiates. And so a small black hole will just actually spew out a whole bunch of things and evaporate very, very quickly. It's only when you get to the really, really large astrophysical black holes that you get black holes that are cool enough to hang around a long time and suck other stuff in. So it's a temperature thing.
And it seems like, David, you were going to jump in earlier, so would you like to add?
Maybe I'll just point out that I'd like to connect to the question more specifically. It's you really don't want to think of things coming out of black holes. I don't think that's the right way to think about this. And this is really a combination of theories. It involves quantum physics and general relativity. So this is really what Stephen Hawking was famous for, because what he did was to take what are called quantum fields, in a region where space is curved, and show that you have things happening just outside of black holes that can look from the outside like things radiating off a black hole. But it's not a sort of purely curved space-time general relativity effect. It's a combination of things, right? And that's what Hawking really got us to.
Okay. Here's another question, and I kind of want to know a definition. Excuse me, a definition first. Are any of the panelists quantum realists? And I kind of want to know what in the world that is.
Maybe this person is referring to the idea that the wave function is describing reality directly. There are some ideas in which you can take the wave function. Normally, when we study quantum physics, we think of the wave function as not being directly physical or observable. That you can get something physical from the wave function, but you have to do some not terribly complicated calculation. You have to take the modulus squared of the wave function. But the wave function itself is not physical. And there are some ideas that the wave function is physical. I think that's maybe what the person is asking about. And I don't know how to answer that.
If that's what they're asking, I would think that's very doubtful. Here you start getting into people's prejudices about what direction to go is the better prospect. For a while, I played with ideas not with wave functions, but with Wigner functions as possibly currents. But honestly, I never got that to work either. So what we have right now is whatever basic object you're using for quantum mechanics, and this doesn't have to be a wave function. These are just descriptions. They're not necessarily something that directly maps onto what's out there, which is okay.
So there's another question I've also found quite interesting. Is modified Newtonian dynamics a viable alternative? I don't know what that is.
I mentioned a little bit earlier that one option other than dark matter was to modify your theory of gravity. This is what it's referring to.
Okay, that makes sense. So yes, the answer is yes then.
Well,
or
sort of,
potentially.
yeah. It's not dead, but again, you will notice from what my observational astrophysics colleagues are saying, they're very comfortable talking about dark matter as a reality. Currently, the judgment of the astrophysical community is that modifying gravity is a very remote prospect compared to dark matter. That's the gamble we're taking anyway.
So I don't know what
I would like to add, yeah.
Go ahead, John.
I would like to one more thing is that till now we have been talking about dark matter presence in galaxies, but it is possible in future. Like I guess we already have few or even one case where we really don't need dark matter to explain the galaxy matter content. So I think till now we think that okay, dark matter is the norm, but maybe in future with increase in observation, maybe the dark matter presence can be an exception. So we may have most of the galaxies without need of dark matter as well. So we have to see where observations will lead us to.
Okay, I have two more questions because I know we're getting to the top of the hour and I want to be respectful of all of your time. But there were two more questions that I was hoping we could get to. This one is, I found it quite interesting. He admits it's a bit tangential, but would like to ask, what's the scoop on eternal inflation, and can it really be said to produce an actual multiverse? Now, I know, first of all, that you guys are observational, but I think that this is quite an interesting question, and I was really curious if you had any thoughts on this, and it kind of led to the second question that I had, and I was wondering if there's any evidence that black holes may lead to actual multiverses as well. And
Maybe
again,
I'll
because
put,
you're observational, like everyone gets quiet because you're observational.
maybe I'll connect to the last part,
Yeah,
Sunny,
yeah,
that you mentioned black holes. There's some interesting mathematical solutions. You know, if you play around with particles, you drop them into black holes, and you follow them mathematically, you can find some strange solutions. You know, like you can drop in light particles one after the other, and you'll find that these things they're going inside of a black hole, and you can follow them mathematically deep into the black hole before they reach the point where the mathematics falls apart. And what you'll find is that these things are moving away from each other, and so there seems to be a sense in which, you know, just before you can no longer follow them anymore, they're so far apart from each other. And that's a very strange thing, because you're inside of a black hole, and you know, from outside the black hole, this looks like a finite region. It could be pretty big. You know, some black holes are pretty small. You know, they're a few times the mass of the sun, but contained within a small region. Yet the math is telling you that these things that are inside the black hole are very, very far apart. And so that sort of goes to your question about what's happening inside of a black hole. Are you entering some other strange region? And so you have some strange mathematics there that you can appeal to.
Anyone else want to add anything to that?
Yeah, in physics and cosmology, when you're at the cutting edge like this, and when your theories are not very well constrained by observations, you can very easily get into exotic ideas, and multiverses are an example of this. In many approaches to cosmology, especially quantum cosmology, multiverses almost seem like an idea that's very difficult to get rid of. You just get multiverses dropping in. Eternal inflation is just one version of them. But also, this is an area of physics where the ideas, everybody knows that they're very, very speculative. And it's extraordinarily difficult to imagine ways where you can get evidence for these, properly speaking. So yes, these are interesting ideas. They might even one of these days get to the point where they're going to help solve real problems. And there's nothing wrong with a multiverse idea. They're interesting. They're worth pursuing. But you do have to keep in mind that these are very, very speculative as well.
I'd like to point out that, sorry.
No, go ahead.
I just want to point out that the people who propose these ideas would complain that what they're doing is just looking at the math. You know, we take the math seriously in so many places, and then we use this math, and we find that it actually describes things that are out there. And these people would say, look, all we're doing is looking at the math, and they're finding these things in the math. It's not like they're just saying, well, maybe there are many universes, maybe there's a multiverse. They're seeing these kinds of structures in various different kinds of mathematical places. So that's how they would defend themselves.
Yeah, and that's defensible, as long as you remember that these are not ideas that are very well constrained by, say, observational astronomy. And I think sometimes it gets really interesting, because some of the really crazier, if you want, multiverse ideas, you really don't know how it's even possible to constrain these by observation. So you start looking for evidence that's not direct evidence, but you start doing sort of statistical physics with populations of universes and things like that. And often you actually get into interesting mathematical pathologies that even that breaks down. So if you're interested in the philosophy of science, there are actually very interesting examples of theories that almost get pathological. Whether they will ever give us something concrete to explain a real astrophysical observation, who knows?
I would also add to that there are people who would say, look, the evidence is there. It's right in front of us. When you look at an interference pattern, that's the evidence for a multiverse.
That's cheating.
I'd also like to say, I think this goes back to the question that someone brought up of how does the math translate to something into reality? And I think throughout our discussion, you're seeing this circular loop, that you have this really amazing crosstalk between what does math say is possible and what do we actually see. And that's why you need both sides to be able to predict something because you can refine each of the others. So it's great to have both sides going out and saying, oh, what is possible? Oh, the observationalists say, oh, I found this really cool thing. Tell me why that exists. Or the theoreticians say, oh, wow, this is really cool possibility. Do we actually see that? So
yeah, without that interaction, without that sort of positive feedback loop, you really don't have any reliable physics. That's what we depend on with everything.
Just to connect to that, Einstein never really believed in black holes, despite the fact that they were in the mathematical structure that he put together. And he said, no, there must be something wrong there. These things, really don't form. So
I find it so interesting that earlier, a couple of you had said, first of all, in every universe or galaxy that we know of, there's a black hole kind of at the center. So it's a very common part of our universe, and yet it's one of the least known, besides dark matter, the least known realms of our reality. And it's so exciting to even think about those things. I wish I could dive more into it. I really want to know. I mean, I keep thinking, okay, is the black hole the gateway to true infinity? Or, there's just all these cool things that have to do with these black holes, and also with dark matter, because it just seems like there's so much of it, and how can we know so little about it? And yet it's like our view of physics, or everything we know about physics, kind of ends at the singularity. At least that's what I understand. At least that's the common, what lay people think. I may be wrong on that, but it's like, I want to know more. I mean, can we not just dive in there and find out what it is?
Sonia, I just want to point out. Sorry.
Go ahead, please.
No, you were saying, black holes were these very abstract kinds of things that were in the mathematical structure, and nowadays they're all over the place. They're very practical. For example, Duccio in his thesis, I don't know, you have hundreds of black hole masses in many different galaxies, right? This is part of Duccio's data that he's analyzing. He has actual, the masses of many black holes. So maybe you can tell us about, how massive these black holes are.
Yeah. We know that almost every galaxy, hosts a supermassive black hole at its center. Supermassive means that we are talking about millions up to billions of solar masses. So at the center of every massive galaxy, we have these huge black holes. And in some cases, we know that these black holes are accreting a lot of matter, so much matter that they produce a lot of structures around them, accreting structures. And these structures, so the matter that is falling in the black hole direction, we are talking about a very tiny part of the entire galaxy. In this tiny part of the entire galaxy, there is a huge quantity of gas, stars, everything that is falling through the black hole. And so we can find a lot of different structures. We can observe different structures, such as accretion disk around the black hole, such as clouds of gas orbitating around the black hole. The most internal part nearby the black hole, so in the most innermost part of the black hole, there can be produced also powerful jets, which means particles that are launched with speed up to the speed of light, and that can reach up to million of light years far away from the site where they are produced, nearby the black holes. So we know that a small percentage of these black holes can produce so powerful events, and this is also a proof of the existence of such supermassive black holes at the center of almost all massive galaxies, because we can observe so much power in so much tiny region.
Oh my gosh. I am dying here because now we've opened up a whole new bit of questions, but we've already gone over time. Oh my gosh. Okay. So I'm going to try to rein myself in because now I have even more questions and I'm going to try to stop myself. So, what I would like to do is give you guys kind of your last word. And I want to thank you guys for coming on, but I'd like to get your last thoughts on this. So, Chandra, I'd like to go with you first.
Yeah, so I would like to add this: black holes are not only in the center of galaxies, but it is scattered all over the place. So actually, if you think about black holes, they are in different kinds of masses. So Duccio mentioned about like million to billion, and there are black holes from few times solar mass to thousands of solar masses. So those are scattered. You can find in random places in the galaxies. And another question that I saw recently just now is somebody wants to die getting to the black hole, but it is not easy because we don't have enough fuel to reach there, and our Earth is located in such a way that we are not going to interact with the black hole in any case, and also we cannot travel there to get sucked into the black hole. So we are safe here, I think.
Really quick, I got to ask one question. Is our closest black hole the one that's at the center of our galaxy, or is there a black hole even closer?
I think the supermassive ones, yes, but I think there are some which are less massive ones, might be closer as well. But I don't know from observation which is the closest one. I don't know.
Yeah, the deadlier ones are a lot closer. The smaller ones are a lot closer.
Oh my goodness! I just I like having more things.
Yeah, but my point is that we don't have enough fuel to reach there. We don't have the technology which can make us reach there. Okay.
Maybe I should point out, maybe these would be my concluding thoughts, that Emily just wrote a paper on comparing the small black holes with the supermassive black holes. And we think that they're sort of similar. And Emily just wrote a paper on that. I was actually reading that today.
Oh my gosh. Okay, so I'm going to have to read that now. Is that something I can access, or do you have to be in?
Sure, you can access it, yes.
Okay, I really want that. We've actually had a show on black holes. I feel like we need another show on black holes now because this is just too exciting. I have so many questions. Okay, Emily, I'm going to go with you for your last thoughts.
Yeah, I think it's been a really interesting discussion overall. I think I found it very interesting that we have this spectrum of physics and math. And there are those of us that like to very much stay and talk about what we can see and what we have seen. And then there are those of us that also like to explore with math and such. And I think it's just really a beautiful thing that you have this full spectrum. And I also really love that the crosstalk between the two of what do you see, what's possible, and then bringing those all together to predict something. So, yeah.
If I was in this field, I would be total ADHD. I would be going into so many different directions. I'd probably get nothing done. But that means that I get to live vicariously through all of you and maybe kind of keep myself reined in a little bit. Tanner, I'd like your last thoughts.
Actually, I'll throw up a question. I'm sort of curious because when I teach non-science majors and science majors but not physicists and physicists, everybody seems interested in black holes in particular. So there's an interesting cultural question over here. How did black holes become one of the sort of leading sexy topics in modern physics? I mean, I really don't know. So there's a sort of fascinating, psychological, sociological, or whatever question over here too. I'd like to know.
That is such a good question. I will say that I think, the unknown. We've heard things about this spaghettification of things, or how you get to a certain point and time just stops and then thinking about what is on the other side. It's like a doorway that's open and yet we can't see. And so all of those things kind of make the part of our brain that's, it's always searching for the next thing, the next, we want to get to the bottom of the ocean, or we wanted to get around the world, and we wanted to get into the big sky. We wanted to get to Mars. We wanted to get beyond our solar system, and that's kind of our next frontier in a sense. I kind of think that's, at least I think that would be my opinion anyway.
Okay. Well, my students certainly love black holes until I ask them about it in an exam.
Yeah. Good point. Good point. Duccio, I would love. Oh, sorry. Go ahead.
Yeah, okay. I would like to add that I think the most of the time people are occupied with the idea of something like monster or devil. So in a way, people take black hole as something that will just come close to you and just suck you inside itself. So I think this is just some kinds of fascinating to think like how it will happen. So I think that's why people are drawn to this topic. However, it is not superficially it looks simpler, and of course it is the simplest object we study, which is of such on such big scale in terms of mass. So yeah, I think it is interesting. Yeah, thanks.
Thank you. Duccio, I would love your final thoughts as well.
Yeah. I wanted to stress again what Emily said about the connections that we need in astrophysics and in physics in general, because the more the technology is going deeply and deeply, we have a lot of technicians, we have a lot of observationals, we have a lot of different people working in different kind of field of physics and astrophysics. But the real discoveries, the real interesting stuff comes when we talk each other, when we combine theory with observations. So this positive feedback, positive loop, which is always compare what we see, what we expect, what we theorize. This is the main focus of our research. A multi how to say multi approach, I would say.
Can I also just say, and we're not just talking about this, like this is how I came to know David. Look, he does a lot more thinking theoretically, and Duccio and I do a lot more observing. And he came to a collaborator and I said, oh, I had this idea, and from what you saw, let's write a paper, let's do collaboration. So we're not just saying these things, this is what we actually do.
And to make that even more practical, I should point out that Duccio is right here in front of me. So I'm a theorist, he's an observer, he's right here across my desk. So
Oh my gosh, that's awesome. So in my world, we call it multidisciplinary. So we all have a common goal in a sense, and we can get siloed if we're not careful. So you get on this multidisciplinary, and you can do better work that way. Break down those silos, think about things in a new perspective, and that's what I'm hearing from you guys. So it's really cool because multidisciplinary teams and multidisciplinary work is what I do every day and what I love and I'm passionate about. So to hear it from other perspectives is great. So first of all, I want to thank you guys so much. We went over time and you guys were gracious. And I want you to know, I do respect your time and value your time. And I don't like normally going over, but I will tell you that I'm geeking out completely. And I feel like we're just getting started. It's like we just got warmed up and now we have to stop. So thank you guys for staying and for doing this. I really, really appreciate it. For everyone, I want to thank you guys for staying with us, for asking your great questions, because we honestly had some of the best discussions from the audience as well. So I want to thank everyone behind the scenes that makes this possible. We have great people, and I know there's actually been some new ones who have come on, and I need to add them to my list. But for right now, I'm going to thank Wes, Josh, Phil, Kat, and Jenna. And thank you to all the new ones as well. I want to tell you guys, we have other shows on here. We have Secular Soapbox, Women Atheist Unloaded, which I am also on Saturdays. We have the Sandbox Debates, One Good Reason, and The Bible Says What. So check out all of the other great shows. If you want to support us, there's some really simple ways you can. Hit the like, hit the subscribe, hit the bell, share it, comment on it. All of that helps the algorithms. But if you want to really help us, go to our Patreon account, and something as simple as $1 a month can make a big difference in the work that we do. So thank you guys all. One of the things that I love about this show is we're not just talking about atheism. We're not just talking about secularism. We're not just talking about secular humanism. We're talking about real world things, science, logic, reason. And it just warms my heart to do this. And I'm so grateful that I have the opportunity to be a part of this show. So thank you all. Thanks to our guest. And until we meet next time, remember to think critically. Good night, everybody.